I will speak about the problem in the title of this paper of locally decodable data compression. And the motivation for this talk is kind of large-scale digital storage. So as we all know, modern storage or cloud storage is facing two conflicting traditional challenges, which are kind of exacerbated in the modern AI era. On one hand, the explosion of digital data being analyzed and uploaded on remote servers like the cloud motivates very aggressive compression of similar data sets in order to save on communication costs and communication bandwidth and on storage costs. And on the other hand, with the rise of AI and kind of prediction and training of algorithms, we know that a lot of AI-based technologies require continual access to the data, and they require more and more sophisticated search capabilities over compressed data. So the concept of archives is kind of less relevant these days, even if not scanned by human beings. It is much less stale data than traditional, than it used to be. And motivated by this problem or question, we study the following data structure problem, which we call locally decodable source coding. This is based on a joint work with Emmanuel Viola and Huaqing Yu from SODA 18. And in this information retrieval problem, we need to build a data structure as follows. So think of so here's the problem, which is kind of the cleanest toy example, which models this trade-off between time and space. So an encoder, let's say a Dropbox server, wishes to store a collection of highly correlated files, data sets x1 to xn, which is jointly distributed in a way using as cheap as possible memory space, ideally the information theoretic minimum number of bits, so that each individual file can be retrieved very quickly, ideally with constantly many IOs or cell probes on a word RAM. And what do we mean by correlation? So in this distributional version, the information theoretic minimum space is just the joint entropy of bold X, which is the entire collection. And by correlation, we mean that the joint entropy is much, much smaller than the sum of marginal entropies. So throughout the talk, think of the joint entropy of our distributions under consideration as being, let's say, a factor of 100 smaller, or even super constant smaller than the sum of the marginal entropies. And our model of computation is the word RAM. So this is the standard model for data structures. So the space of the data structure is just the number of cells. Each cell can hold a word, which is typically log n bit words. Log n bit cell. And the query time is measured in the number of cell read, or ideally the actual complexity. So the thing we care about the most is the number of cell probes, the number of memory accesses required to retrieve the answer, but we will actually shoot for, computationally efficient decoding algorithms. And the crucial aspect of the cell probe model is that it allows constant time operation on these log n bit words. Right. So as most of you probably know, this problem is essentially a distributional version of the classic dictionary problem, which appeared a lot in compressed text indexing, and many speakers, even in this session, like Gonzalo and other people here, I'm assuming we'll talk about. So starting from the seminal work of Lempel-Ziv and Burroughs-Wheeler, Transform, and so forth. So this work is somewhat different in the non-asymptotic and distributional sense of it. And I hope it will become clear why the data structures we propose here will outperform those counterparts. By the way, feel free to stop me if there's any question in the middle. All right, does the problem make sense? All right, so for any such distribution mu, there are always two naive data structures we can construct. So if capital H is the joint entropy, which, as we said, is much less than n words, or n log sigma, where sigma is the alphabet bits, then using Huffman or arithmetic coding, we can always compress the entire collection down to the information theoretic minimal space, age plus 1 bits. And this is, of course, optimal. Unfortunately, the decoding time will be then a full linear scan. And the reason is that, this is the nature of compression, right? Once you take, if you want to exploit global correlations and similarities across data, then compression is essentially a packing argument, right? It inherently destroys all the locality of the original coordinate system. And a nice example, maybe to exemplify this, is singular value decomposition, right? When you take a data set and you change a basis, then the original coordinate system doesn't make sense anymore. There's the original kind of information in every bit of the compressed code word contains information about all the coordinates, and that's just kind of inevitable. This is an inherent feature of compression. Of course, the other extreme is to do what essentially Dropbox is doing today, which is to compress each file independently. And then, of course, the problem is that you're paying the sum of marginal entropies, which again is much, much larger than age. And the upshot, of course, is that decoding time is constant. Does that make sense? Again, feel free to stop me if there's any question. And basically, the main question in this talk is, does there exist a better time-space trade-off? And more precisely, our main question that we pursue in this work is, what statistical properties of low entropy joint distributions enable efficient locally decodable source coding schemes, where by efficient we mean with, let's say, a constant space overhead, or ideally even succinct space. So ideally we would like a constant or polylog overhead over additive overhead over the information theoretic space benchmark. And the decoding time will be said to be efficient if it's polylogarithmic. And again, ideally we would hope for constant query time, which is kind of the dream on a word RAM. Any questions? All right, so unfortunately, and probably not surprisingly, it's not hard to show that for most joint distributions with low entropy, those two naive data structures are essentially the best you can do. So, in a sense, we prove in a formal sense that the LDSC problem is a complete data structure problem in the cell probe model, in the sense that for any data structure problem, you can basically embed it into some weird low entropy joint distribution, where basically the files, the XIs, correspond to the n queries of the data structure problem. So think of your favorite data structure problem. You can encode the answers to all the m queries as your collection of files, and the entropy, the joint entropy of all those answers is, of course, the entropy of the database, of the data set, which is typically much smaller. So this shows that, just by counting arguments or cell probe lower bounds, which I worked on, that for most distributions, you cannot do anything. And the question is really what, for which distribution can you, low entropy distributions, can you do something interesting? And in fact, even for independent random files, which seems like the trivial case, right, where independent compression is optimal, even then it's not completely trivial, right? Because if you have your files distributed independently and uniformly over an alphabet sigma, which is not a power of 2, then Huffman coding, or basically storing independent compression, will lose at least 1 bit per block per file. which means that you have n bits of redundancy over the information theoretic minimum space. It turns out that there's Dodis, Patrascu, and Thorup in 2010 managed to overcome this problem, and they gave this really beautiful succinct dictionary data structure, which has only a single one extra redundant bit over the n log sigma bits of entropy, and it manages to decode each file in constant time. And the technique here is really what's impressive. They kind of managed to cook up this locally decodable version of arithmetic coding by introducing what they call A-B trees, or which are essentially compressed B trees. So those B trees are compressed where kind of the children of every parent node is stored conditioned on the information in the parent node using a very clever recursion, which I won't have time to elaborate on. But the point is that even though this sounds like a minuscule problem, right? You know, it's just one extra bit or n extra bits for the independent case. This DPT data structure will actually play a crucial role in our more complicated distributional case. Right? Questions so far? All right, so the main focus of our talk, you know, we kind of ask ourselves, okay, where should we start? What is a natural joint family of low entropy, you know, a family of low entropy joint distributions? And I guess the simplest example is the class of Markow chains, right? Where you have, let's say, n random variables, you know, drawn from a Markow chain on a finite state space. And kind of the simplest subcase of Markow chains is storing length n random walks on d-regular undirected graphs. All right, so we will actually handle more general, any graph, like directed and non-regular, but the focus of this talk will mostly be on the regular case. And again, Markow chains are kind of a natural starting point. They model, you know, time series sequences, financial logs, version control in file systems, time decaying weather reports, and so forth. So many data sets exhibit this, are kind of inherently sequential. And we thought this would be, you know, the first proof of concept that you can do something for, in the non-asymptotic case of kind of a natural class of correlated files. And so let's be more precise. So you can kind of forget about all the introduction and focus on this clean data structure problem, right? So you have, the goal is to pre-process a random walk of, you know, V1, V2 up to Vn, which is just a random walk on this, for starters, a d-regular undirected graph. And the goal is to pre-process this walk into a cheapest possible data structure in terms of space, so that queries of the following form can be supported. Given a time step I want to know which vertex did the random walk visit in time step I, right? So for example, you get the index 117, and the goal is to return you were in vertex number 47 at this time step. Does that make sense? Right, and so what is the space benchmark? So in the simplest d-regular case, suppose we start with kind of a uniform initial vertex without laws of generality. So you accept this first, the cost of describing the first vertex. Each vertex can be described optimally using only log d bits of storage, right? You just store the relative encoding relative, you know, if you were in vertex 48 in step I, and for step I plus 1, you only need to store the neighbor, kind of the relative encoding compared to where you are now. So for example, if d is a power of 2, if it's 8, let's say, then you only need 3 bits. You only need 3 bits per per block, per VI, right? So, and you can actually achieve this information theoretic optimal space up to 1 bit. But unfortunately, by storing exactly what we said now, at least if D is a power of 2, and in fact, even if D is not a power of 2, you can use the aforementioned DPT data structure, which allows you to do this even if D is not a power of 2. But in either case, this will not kind of save you, because when you're storing only the relative encoding of each vertex, which neighbor did I go to in vertex I, if you want to actually know which vertex it was that you visited in step I, there's nothing better you can do than just unfolding the walk all the way down for the start, right? Because without knowing which vertex you started from, you have no idea where you are right now. Questions about this? All right. And of course, the other extreme, again, is to store the actual vertex you're in. And again, the marginal entropies of each vertex is marginally uniform, right? Because we started from a uniform vertex, and the stationary distribution of a d-regular graph is the uniform distribution. So marginally, each vertex requires log g bits of information, right? So there's no way to avoid it. So instead of spending log d bits of information, which is, if d is 8, you're spending 3 bits, you're spending log g bits of information, where g is, let's say, 1,000,000 is the size of our graph. And of course, the upshot is that you have constant decoding time. And of course, you can actually combine these two data structures, right? You can kind of divide your random walk into B-step subwalks, right? And each block of B steps of the walk, you store kind of optimally, right? So you're losing log G minus log D, which is log G over D, bits per block, right? Because you're compressing each one of them optimally. And this gives you kind of this linear trade-off, right? Instead of unfolding the walk all the way to the start, you're unfolding it only up to the last block benchmark, right? Which is at most B steps far apart, right? So far away. Does that make sense? So the decoding time will be essentially the block length B over the word size, which is log n. So this is kind of redundant. And the redundancy, the extra amount of bits you need to spend compared to the information theoretical minimum space is n over B, right? So you have this linear trade-off of B versus B query time versus n over B space. And as far as we knew, this is the best for Markov chains. This was the best time-space trade-off that existed up to our work. Questions? So our first main theorem, which is still only the toy example that I'll focus on here for the regular graph case, is that there exists a word round data structure that stores a random walk on any d-regular finite graph G using only 3 extra bits of space compared to the information theoretic optimal space. And the decoding time is log n over log L, where L is the number of bits we need to store in a lookup table. So this data structure requires some pre-computed lookup table, which is completely independent of the walk of the input. It's only dependent on the graph G. And in a sense, it can be amortized away, because if we're storing multiple blocks, random walks, or multiple files, instances of this problem, then this pre-computed lookup table can be shared across instances. So really, depending on your taste and application, you can pick L as you wish. But if L is, let's say, root n or something like that, then it's evident that the query time becomes constant. All right, so you're storing only 3 extra bits of space, and the query time is essentially constant. Questions? All right, so let me try to give you a gist of this simple proof, and then I'll say something about the non-regular case and the directed case, which is much more challenging. By the way, Thomas, how much time do I have? Like 15 more minutes or?
I think about 10 minutes plus questions.
Okay. All right. So here's the main proof idea. So consider, this random walk W, V1, V2 up to Vn, which is a random walk starting from an arbitrary vertex on a d-regular graph. The first idea is to chop this random walk into what we call milestone vertices, Mi. So once every log n steps, we designate a milestone vertex, okay? So we have about n over log n milestone vertices, Mi, which are a subset of those VIs as depicted in this picture. And what's nice, there are two nice things about those milestone vertices. The first thing is that, why did we choose them to be log n far apart? The crucial aspect here is that the mixing time, since G was assumed to be finite graph, then the mixing time of a random walk on this d-regular graph is theta of log n, right? A random walk on a finite graph has to mix in theta of log n steps. Because the graph is d-regular, and we know the stationary distribution of the random walk is the uniform distribution, or more precisely, after L steps, your statistical distance from the uniform distribution is exponentially small in L. So if you take L to be log n, you get very close, polynomially close in statistical distance to the uniform distribution. Then you can afford to store those milestones. Those milestones, basically, the point is to convince you that those milestones satisfy precisely the DPT dictionary prerequisites, right? The requirements. I remind you the DPT dictionary was able to store uniform independent files with a single extra bit of redundancy and constant query time. Did that make sense? All right, so the first step of the data structure, pick n over log n milestone vertices Mi and store them using the DPT dictionary. All right, now we come to the more interesting and crucial feature of milestone vertices. So the second feature of milestones is that they break the dependencies across blocks, right? So if you have if we denote by Bj the theta log n block of vertices between Vj and Vj, Mj and Mj plus 1, between two milestones, we have theta log n vertices. Then those blocks Bj, I claim that they are uniform and independent, conditioned on the milestones, right? And this should be, again, intuitively clear, because after the random walk mixes, which takes only log n time steps, there's no longer any correlation between, two consecutive milestones, right? They are essentially independent and uniform in the graph. Does that make sense? And this allows us to store the actual blocks, Bj, using a second level of the DPT dictionary. So in fact, not only can we store the milestones using DPT, but we can also store, in fact, the blocks using DPT, right? So we have about n over log n blocks of vertices. Those blocks are conditionally independent and uniform, conditioned on the milestones, in the sense that, there are roughly d to the block size over g walks with high probability in every block, or it's uniform over this large of a support. And this means that we can store both the milestones and the blocks between the milestones using 2 levels of the DPT dictionary. And I will kind of skip the details due to lack of time, but this essentially, the decoding algorithm is then pretty clear, right? If you want to decode VI, where I is, I don't know, 1023, then you first go to the 2 milestones, you decode the milestones using invocation of the first top level DPT dictionary. And then conditioned on the 2 milestones, you can also probe the second level DPT dictionary to decode the actual block, right? And this only gives kind of a, I was cheating a little bit, this only gives a cell probe data structure in the sense that if you really want constant query time, then you'll only, the query algorithm I just described it requires a very complicated, non-standard operation on the RAM. So if you want to turn this constant query time cell probe data structure into actual word RAM, then again, you need to work harder, and I won't dive into the details, but instead of constant query time, you get this log n over log L query time. And the upshot is that this is a standard, completely fair word RAM data structure. So, and this kind of summarizes the gist of the simplest regular case. For non-regular and directed graphs, the problem becomes substantially more challenging. And the intuition is the following. First of all, and these are kind of 2 related problems, the stationary distribution of a random walk on a non-regular graph is no longer uniform, right? It's something, arbitrary kind of. And a related problem is that the number of subwalks between any 2 milestones is also varies. It's also not fixed, right? You can have like imagine a graph which is kind of an expander plus a path or something, then of course that the number of random walks or the support size of between 2 consecutive milestones can be very, very a lot depending on the actual milestones. So what was nice in the regular case is that regardless of the actual milestone, so you fix the milestone, let's say 24 and 57, it doesn't matter. The number of random walks or the support of random walks between any 2 milestones is exactly the same no matter what the milestones were. And in the non-regular or directed case, it's completely, this completely fails. Okay, hope this makes sense. And intuitively, what those 2 challenges mean is that if we really want to match close to the information theoretic optimal space, then we really have to use variable length coding. So variable length coding in the sense of, Huffman coding and so forth. And this makes constant time decoding extremely more challenging because, one reason is that when you're using variable length coding, then the memory locations of substrings that you wish to decode are no longer predictable, right? Because the memory locations themselves depend on, it's a random variable basically. So there's a lot of work into resolving this issue. So this is the theorem we prove for general graphs, either non-regular or directed. Essentially, it's the same result, very similar result. We can have essentially the same, pretty similar time-space trade-off. Oh, I wrote here d-regular. This is, of course, a mistake. So this is for general graphs. We have a data structure, a word RAM data structure that stores n-length random walk on any graph. So this should not be, so D, you can think of D as the average degree. Anyway. And the redundancy is only log n bits. Unfortunately, the decoding time becomes logarithmic. It's no longer constant or log n. This time it's log n. But we show in the paper that, in fact, this log n seems inherent here. So if you manage to improve the log n query time here in the general non-uniform case, then this would imply a dramatic improvement to, to a long-standing problem of Petrascu, and he even mentioned it in his obituary. Thorpe even mentioned this in his obituary, of breaking the log n query time barrier for succinct dictionaries, the classic problem. So log n seems pending, kind of a big breakthrough on succinct dictionaries. This seems the right answer. Yeah, I won't say much about how we handle this variable length coding. I'll just say that basically what we do is we take the milestones, and we don't only store the milestones, we also consider subwalks which are close to the milestones, and we're basically bundling in a very clever way, which is kind of resembles a rejection sampling procedure. We basically bundle subwalks in a way that basically partitions the walks into uniform sets, and then we can basically reduce to the DPT case. But this is much more challenging and less cleaner than what I said now. Final remark is that I just want to say that the assumption throughout our work that the graph is finite is kind of essential, right? So if you look at our locally decodable source coding problem, the random walk problem, on the n length cycle, so it's a cycle of length n, it's not hard to see that storing a random walk on the n length cycle, length n cycle, is equivalent to the so-called partial sums problem, to 1D range queries or partial sums, for which there's a log n over log n lower bound. So the assumption that the graph is maybe not constant, but not super large in terms of n, it's crucial to achieve our results in the first section. That's it. I want to conclude by mentioning future directions. So, Markov chains were really just, the tip of the iceberg. It was just a proof of concept that the LDSC problem does admit non-trivial trade-offs for natural distributions. And the next natural step is considering more complicated graphical models, for example, low temperature easing models, which are motivated by physics applications and so forth. And a question I think is interesting is considering low entropy joint distributions, which are obtained as the outputs of deep neural networks, which exhibit, tons of correlations, but the distributions are kind of very opaque and unclear. So is there like a way to formulate this problem? That's it.